good, great. Good afternoon, everybody. My name is Laskar. Before, thank you for feedback and all the chairs, Dr. Yom, Dr. Kim, and of course my colleague, Dr. Oja as well, for inviting us in this feedback webinar. Actually, Dr. Yom and Dr. Oja is my big seniors. Of course, they are really nice guys. So I hope it can be not only become a reunion, but also we can have a good discussion here. Okay, so my topic will be the implementation of multi-loop coils, multi-loop coils for a low profile wireless power transfer system specifically in AGV applications. So you need to know AGV stands for automated guide vehicle. It's something like a robot, mostly used in the logistic, like a warehouse or some factory or manufacturer applications. Okay. So first, I want to talk a little bit about the background motives of the wireless charging trend in the AGV applications, why we should be use this kind of technology for AGV. The first, we can reduce the cost for labor. We can reduce the labor cost and save time duration for the charging. So usually we need some guys to stay in the charging area and do the plug-in during the charging, during the AGV charging. So by using the WBT, the wireless charger, we can cut the cost for the labor and change into the fully automatically charging. And that means that we also can reduce the backup batteries and AGV, because for single AGV with a single battery can run for a more long time compared to the traditional one. Yeah, and also we can improve the safety concern because we can avoid the plug-in sparks, and some human error issue, of course. And the other is just like a derivation from all the three advantages. It's like we can exploit the AGV by forcing it into the 24 hours works and also enable the motion chargings. I think this kind of applications has been presented by Dr. Oja previously, the dynamic charging or the motion chargings. That means the robot can charge while it's moving. Okay. So in the product perspective, we can see what should we use to enable the robot to become a wireless charging robot. So we need the four main components here. Yeah, the first is the receiver converter and receiver coil. These two things will be put in the robots, like in this video. We put inside the robots. So this coil will receive the power from the transmitter, and then this receiver power converter will convert the signal get from the coil into the power that that can be ready to charge the battery, like the charging scheme and protections and many things. Okay, and in the ground side, we have the transmitter power converter here to convert the AC power line into the high frequency AC to be able to resonate in the resonator's coupler here in the coil. Yeah, so total we have four key components here: transmitter converter, transmitter coil, receiver coil, and receiver power converter. So this is a kind of typical advantage from all the products that will be offered from any kind of wireless charger vendor. They will offer, as high efficiency as possible, as small size as possible, and of course the cheapest price, something like this. Okay, so in my presentations, I want to be more focused on the method, like a research methodology. Yeah, the first. The background will become the problem coming from the heat problem, because every guy will buy the wireless charger will ask, how hot is it? Yeah, because they will concern a lot of the heat problem, and also the price and the efficiency. Yeah, but the heat is the most, considerations that the user will think about. Yeah. So for example, in the typical size of the AGB coil wireless charger, it's like a 20 by 10 centimeters. Yeah. In our lab, we test in, also the typical wire here. We call this a leads wire. It contains a lot of strands wire because we try to reduce a lot of, the eddy current and the proximity losses by that. Okay, so by using the typical size and the typical specs of leads wire, we can get a really big heat conducted in this coil. Yeah, and it is a really big problem. Every user will really consider about this. Yeah, so what's the impact of the heat problem? The first, it can reduce the power efficiency, of course, because the coil itself can dissipate more power because of the heat itself. And then it can harm the coil enclosure. Most of the enclosure was made by the plastical elements like PC or ABS. That means the heat will have a big trouble for that kind of materials. And of course, the heat also can harm the AGV robots. Yeah. Then what's the main solution for many kind of vendors to deal with this kind of problem? Yeah, they will do the cooling solutions. Yeah, the easiest way is just put a bulky fan like this. They will put a lot of fan, but this also have another disadvantage. The first, it requires a significant space. Yeah, it consumes a lot of space. It means it will reduce our power density. Yeah, and then also it requires more cost. Yeah, to put in, and also consume more power because the fan itself need the power to run. Yeah, and most of the fan need the some waterproof certification like the IP68 or IP65 and so on. Yeah, so yeah, this solution also have another problem to deliver with. So in this research, I try to find the advantage of the multi-loop coil related to the heat. Yeah, so I think all of the attendants here have a many experience in like a magnetic design, like a transformer or even the coils. Yeah, we know that now multi-loop topology have promising advantage. So let's say we have some design. Yeah, we can make some topology based on the multi-loop coils in the single coil of the wireless power transfer. But how to ensure that it can work well? Yeah, so this research, we proposed 3 steps with the two proposed methods. Yeah, the first is the approach, the geometrical-based approach to estimate the coil key parameters. So by using this approach, we can know the key parameters of the coil so that we can predict the performance of our coil without using like a high specs a computer with the high spec software like Maxwell, SolidWorks, and so on. Yeah, and then after we got all the coil key parameters, we can use all the parameters to do the mathematical based analysis. Yeah, before Dr. Oja have explained about the MFHA, first harmonic analysis, and then we can try to have a little modifications. So I called here modified FHA. Yeah, these are kind of tools for the circuit analysis to see the performance of our resonators, of our total circuit of the wireless power. Okay, and then based on 2 proposed methods, we can do the loss approximations and some experiments to validate the proposed concept. Okay, so the first will be the geometrical based approach. It's quite simple actually. We refer to some old formulas about the magnetics, coil related magnetics formulas. Yeah, for example, like it has been proposed by Mohan. Actually, he also some modifications on some basic equations based on Wheeler and current sheet. I think most of you know about this, and offers a good simplifications. and also good enough accuracy. Yeah, so this kind of the Wheeler one and the current sheet. So we can see here, each formula have the coefficients. Yeah, this is the main contribution from Mohan. He proposed the coefficient, like in Wheeler, you have a K1, K2 here. And for the current sheet, we have the C1, 2, 3, and 4 here, all the coefficients. And the other parameters will be related to the geometrical specs, like D here is the average diameter. Yeah, it's really easy to compute. And also the rho here means the fill ratio, means how big the empty space of the coil refer to the whole space of the coil. Yeah, so rho here is D out minus D in over D out plus D in. Yeah, so both methods also consider a lot of a coil shape. Yeah, so like a square, hexagonal, octagonal, and circle. So every shape have its own coefficients based on the Wheeler or current sheet method. Okay, so another is the mutual inductance considerations. One of the powerful formula is the Newman. We see here is the basic Newman formula. That basically it will integrate all of the all of the surface of the first coil related to the second coil. So have a L1, L2 here. Yeah, so in this research, I tried to combine Archimedean coordinate to put into the Newman formula. So Archimedean coordinate is we can simple to call it as the spiral. Yeah, spiral is different with the circle. Yeah, so we should have some modification on this Newman to put some Archimedean coordinate inside. Yeah, so it's kind of mathematical derivations. Yeah, so these are final equations. Yeah, so before we define all of these Archimedean's coordinate with the pi, big pi here, big pi in and big pi out, and A here is S over 2 pi. S is the screw pitch. Screw pitch means the distance between one winding into the beside winding. This is screw pitch. Yeah. So everything will be integrated based on the big pi, but we don't like big pi because it's not a kind of a specific length. So we need to convert it into the small pi. So we do some Pythagorean mathematics here, yeah, to convert into the small pi. So it become a pi 1, pi 2 here, and substitute into the best Newman formula, and we got this. So we can do the integrations with any kind of, mathematical platform like a MATLAB, like a MathScat, and so on. Okay, so the first approach will be the effective permeability. That means that normally we just use one kind of constant mu or permeability here in any kind of magnetics applications, but we should break down it according to which place the loop, the flux linkage loop pass to. Yeah, so for example here, this is the cross sections of the one loop coil. Yeah, simple one loop coil. This is the circle one and this is the oval one. Yeah, so we can see this is the flux linkage. It passed through the magnetic materials. Here we use the nickel zinc or manganese zinc, yeah, many kind of materials of ferrite, and then pass through the FR4 PCB here, the yellow one, and then it passed through the air. Yeah, so we should calculate the the total closed loop path of the flux linkage, and then we can approach the specific value of the effective permeability. So we define it as the mu effective here, mu effective. It's really simple, just derived by this. We know that the reluctance is 1 over mu times L over A is like it's equivalent with like a resistance. Resistance is rho L over A. So rho is kind of equivalence with the 1 over mu like this. Yeah. So based on this, we can derive it to a bigger form like this. So we separate, the ferrite area and the air area. So we can calculate by using this coil geometric to get the L ferrite, L air. Yeah, and the assumption is I assume the same cross-sectional area of ferrite and air. Yeah, I think most of you will ask, it will not be equal. Yeah, I know it will not be equal, but I do this is kind of simplifications to get an easy approach to the first one. Yeah, so actually I make some derivations why this makes sense. Yeah, make some derivations based on the Maxwell and the Gauss, one of the 4 main Maxwell equations. Yeah, but this is the final form, like this: mu effective equal to mu r, mu o, and over all the geometrical parameters. And based on the coil I made here, so I define this like a single loop coil, the circle one and the oval one, and also the multi-loop. I try to investigate 2 kind of multi-loop. The first one is 2-loop coil. You can see I have a 2 circle here, and the 4-loop have a 4 circle here. Okay, so based on this mu effective, we can calculate the mu effective. Based on this formula, we can calculate the mu effective here for each coils. 1 loop small, 1 loop oval, and the 2-loop and 4-loop we can get here. And we can note here that the multi-loop coil, I separate 2 sides of the coils with a different mu effective here. Okay, and the second approach was the cross permeability. So that means normally we only consider all the magnetic materials in the single coil. Yeah, but of course in the wireless power transfer we will work in a coupled coil or 1 pair of coil. It have a two single coils. Yeah, so the magnetic materials of the other side coils will give a significant impact to the other side coil. How to say? For example, I want to measure the primary coil. Yeah, primary coil here, but the magnetic properties of the primary coil is not only influenced by its own magnetic materials, but also influenced by the secondary coil magnetics. Yeah, so I call this by the cross permeability. Yeah, so how to derive this? Also the same. We use some simplifications, and we approach all of the distance. How long distance pass through the ferrite and how long distance pass through the air. And we also break down one by one to get this kind of equations. And then we replace this mu cross, into the mu 0 in here. So in the first approach, we got the mu r from our ferrite and the mu 0. So we replace this mu 0 into the mu cross. Yeah. So based on the second approach, we got the different value of the mu effective. Yeah, so this mu effective is gathered from the first and the second approach. And the third one was the cumulative coupled regions. Yeah, this will be exist in the multi-loop coils, for example, 2 or 4 loops. Yeah, but in this approach, we have some limitations. Yeah, the limitation is the approach will only can be executed in this identical coils. For example, these 2 loop have the same size, have the same specs, have the same lead wire specs. Yeah, so we can use this. Yeah, but if the coil is not asymmetrical, so we need to have another coefficients to work with. Okay, so based on transformer model, we can make a simple circuit of the 2 loop coils. Yeah, so I assume this is the first loop and the second loop. Yeah, and this connected in series and this connected in parallel. Yeah, so we can see how to deal with the basic electrical circuit mathematics like in series, we can plus all together, M12, M21, and all the leakage. We can do the summation for all the 4 parameters. And for the parallel, we can do the parallel operations here, and then do the summation with the, the mutual. Yeah. So the final equation will be like this. Yeah. So we can see here the red region is the M region. Yeah. So this angle actually also by the assumptions. Yeah. But you can see this clearly if you run with like a finite element metric based simulation like Maxwell actually. Yeah. But after we got this specific angle, like this angle, yeah, so we can do all of this kind of cases without the need of the simulation tools. Yeah, so I think I need to talk in the beginning that actually this coil is only in the one side, like a primary or secondary. So that means for one pair, we will have 4 circle in one pair of coils. Yeah, like this. This is the picture when we put all of 2 coils in a pair. Okay, so yeah, based on this cumulative coupled region, yeah, we can substitute all of our geometrical based approach to these equations. This for the series and this for the parallel. It's for the series and this for the parallel. So we can substitute all of the previous approach to that. So we got the final equations like this. Looks very messy, but actually it will be easy if you run this in the mathematical platforms like a MATLAB or MathSCAD. So this the result. Here is the measurement. Yeah, and this is the calculations. This is a topology. So this is like a 2-loop series, a 2-loop parallel, and this when I use the modified Wheeler, and this when I use the modified current sheet, and this when I use the Newman for the mutual inductance. Yeah. So here is the measurement, here's the calculations, and here's the error. So we can see here that all of the approach have a reasonable error. It's no more than 4.5% for the Wheeler and current sheet. Yeah, Wheeler and current sheet for the self-inductance. Yeah, and then also sufficient error like a 5% for the Newman formula, especially for the mutual inductance calculations. Yeah. And then we do the same, totally the same things for the 4-loop coils. Yeah, so you can remember last time for the 2-loop coil, we have the simple circuit. So the 4-loop here, we have a little bit more complicated. Yeah, so first we do the series firstly, because the 4-loop coil I have been used in my research. We use 2 coils in series, then connected all of the 2 in the parallel. Yeah, so the cross section will be like, oh no any cross section here, but the side view, yeah, the side view will be like this. Yeah, so we have a 4 coil here, yeah, two pairs in series, and then 1 pair in the parallel. Yeah, so the circuit will be like this, and do the same things to get the the final equations like this. So we can also do the comparisons between the measurement. Yeah, we measure, use the impedance analyzer, and we compare with our calculations results. Yeah, so the same. This is the measurement calculations, and the error is a little bit higher than the 2-loop coil, but it's still reasonable. The error for the self-inductance are under 4 and 5% respectively for the Wheeler and current sheet methods, and the error for the Newman is under 7%. Okay, and then we do also the same for the AC resistance calculations. Yeah, so previously we got the self-inductance, and then we got the mutual inductance, and then we got the AC resistance by using the Ferreira method. Yeah, I think 2 kind of formula is quite popular. One is a dual method, and the second is a Ferreira method. So I prefer a Ferreira here because during my research, this formula offers a better accuracy than the two wheel. Yeah, but it's depend on the researchers. Yeah, you can choose any kind of formula that you are happy with. And then I choose the Ferrara. Yeah, first we compute the RTC here. It's quite normal equation for Ferrara, and then we can also use the RAC and do this mu with mu effective that we calculated before, and then we do the substitution into these equations. Yeah, so here is the measurement versus the calculations for the modified Ferrara. Yeah, this is the AC resistance. So the dash line is the measurement one, and the straight line is the calculation results. Yeah. So this in the single coil, no couple, means that you only measure the single coil, and in this graph is the 3 cm air gap. Yeah, and in this graph is 4 cm air gap. Yeah, I choose the 3 and 4 cm because this is the basic requirement for the AGV. Yeah, for EV, we know that the ground clearance will be very, have a big variations. It's kind of a 25 centimeter to maybe 35 or 40 centimeter, like for the SUV type. Yeah, but for AGV, most of the applications will run in like a 3 until 4 centimeter air gap. Okay. So the second approach is modified first harmonic approximations. So this FHA, first harmonic approximations, I think it has been clearly explained by Dr. Oja before. Yeah, so how to make it modified? Yeah, I just simply put the R core here. So before it's only XM in here in the transformer model, sorry, a T model. So I put the R core here. Yeah, and then we do the approach based on the Bertotti model. Yeah, so we can derive all of the loss analysis by Bertotti. We have the high hysteresis, pH here, yeah, pH, and the PED is eddy current, and PEX is the excess loss. So based on all of the equations here, we can put the R core in this R here, because all of the losses components like hysteresis, eddy current, excess contains the R core. Yeah, so for the mathematical perspective, I make the R core into the polynomial model like this. Yeah, and then when we can derive the same, the same gain curve or gain transfer functions, absolute value of Vs divided by Vp, the same as the FHA actually here, the same, totally the same. Yeah, but we put the R core components, so we can do, the equation like this. Actually, the same, methodology for the derivations. So the first, I do some iterations to get the R core sampling. Yeah, this actually I do by the experiments. Yeah, so we compare the experiments result with the GV MFHA we got from here. So we know the GV at the first time, and then we find the R core, how much the R core, and then we calculate the error, the error calculations, and then we check the error is small enough or not. If it is small enough, we can select this kind of R core. But if the error is too large, yeah, we can do some increment or decrement on the R core, yeah, to get the the best R core value. Yeah. So, and then we got maybe like 8 or 10 samples of R core. Then we put it in the polynomial regressions. So we do the forward regressions, not the backward one. We choose the forward one. So we do the regressions. Of course, we have some parameters like OLS, ordinary least square estimators, RSS and SSR, sum of squares, to to see how good is our regressions. Yeah, so we select from the lower order, yeah, because we do the forward one, and then we run the regressions, and we increase the regression order, the polynomial order, yeah, and we check the SSR and RSS if it's good enough, so we can finish the Harper polynomial regressions. Yeah, so this is the regression results. So red one is the linear, the second one is second order polynomial, and the blue one is the third order, and the black one is the experimental results of the R-core. Yeah, so we can get the second order by these equations. Yeah, and we can get the third order by this one, the below one. Yeah, so based on that, we can compare the operability formulas. So the left side is the basic first harmonic approximations, and the right side is the modified FHA. Yeah, so our experiments will try to compare all of these two perspectives, which one is better. Yeah. Okay, so this is one of the special things about the MFHA, the modified FHA. If you know about any kind of resonant converters, yeah, in this case it's the WBT, yeah, because wireless power transfer is one kind of resonant-based converters. We will get a really beautiful phenomena. It's called the independent load gain, or ILG, independent load gain. That means that we can have a one point here that will remains the same gain no matter we change how big the frequency, the switching frequency. Yeah, so this really ideal, and it's really good, really great, because we can keep our resonant converter in the resonant points. Yeah, and we, no matter we change the load or we change the Vin, it can keep the same, gain, the voltage gain here. Yeah, maybe for the basic methodology for the resonant-based converter control is we change the frequency, frequency modulations to regulate the output voltage or current of our switch mode power supply. Yeah, but if you achieve this independent load gain, means that you can fix this frequency. It means you can achieve the higher frequency by that. Yeah, but this is a kind of the fairy tale. Yeah, it's not. Actually, it doesn't exist. Yeah, maybe if you try to make your own resonant converters, especially for the wireless power transfer with the big leakage. Yeah, so the frequency will be very sensitive. Yeah, so MFHA will explain that the independent load gain ILG is never happen. You can see here have the bandwidth. We have a non-ideal condition here that there is no one point that remains the same gain for different maybe different power or different load conditions. Yeah. Okay. So here's the experimental validations. The first, based on the geometrical-based approach, we can calculate the power loss. We can estimate the power loss. Yeah. So we divide into two kind of the losses. One is conduction and the core. The first one for the primary side and the secondary side, and for the total. T here means the total. Yeah. So we can break down of the loss based on this formula. So we got here this for the air gap 3 cm and this for the 4 cm. Yeah, we have the conduction for primary, secondary, core loss for the total core loss, and also the coil loss for the primary and secondary total. This is the total coil loss, means the conduction plus the core. Yeah, conduction plus the core. And we can compare between all of the coil here, one loop, two loop, and two loop in series and two loop in parallel, and also our 4 loop coils. Okay, so we can get here, if we make the multi-loop by a 2 loop topology, you see here the loss is quite big, it's not good enough. But for 1 loop and 4 loop, loss is quite the same, and the same trend for the 4 cm air gap, the same trend. Okay, so we do the 30 minutes burn-in test to validate the these estimations, the power loss estimations. So we do the burn-in. we use the thermal camera to monitor the temperature rising of the coils. Yeah, so this is the one loop. Yeah, the one loop and the two loop series, two loop parallel, and the four loop. Yeah, this for 3 cm, and this and the right side here is for 4 cm. Yeah. So we can see here, for loop coil will offer a better thermal performance compared to other 3 coils. Yeah. If we back into the estimations, 2 loop coils have a bigger P loss. That means that, yeah, this the thermal performance also not good as well. Yeah, but in here, 4 loop coil have a better thermal performance than the 1 loop coil. Yeah, but in these estimations, it looks the same. Yeah, but why 4 loop coils have a better thermal performance? That's because we need to convert all of the P estimations into the P per loop. Yeah, because you have a big dissipations, but you have a longer Leeds wire that compose your coil. That means the dissipate power in the same length of Leeds wire will be smaller for loop compared to 1 loop. Yeah, so all of the P loss estimations, I convert all of them into watt over loop. Yeah, here. So when we convert into this, we can see that, you know, the 4 loop coil have a smallest dissipated power. So that's why we can explain all of these phenomena. Okay. And then this the validations for the MFHA. Yeah, so before we need to build our circuit firstly. This is our hardware. So we have the pre-regulator, have a boost PLC and DC-DC ALC in the front side, transmitter side, and then they have the inverter to convert these power line AC into high frequency AC, and then have a rectifier and the post regulator DC-DC pack to have do the charging scheme to be ready to charge the battery VB here. So this is our hardware picture, and this is our controller. Mostly we can use the frequency modulations or the phase shift modulations in this kind of circuit. We do this based on the F28035 DSP chip. Yeah, and this the comparison of the FHA and MFHA. So the red dashed line here is the FHA, and the blue dashed line here is MFHA, and the black here is measurement. We can see by putting the R core value into the transfer functions, we can get the more accurate graphic compared to the normal or traditional FHA. Yeah, you can see all here. Here is the output power. The output power have a better accuracy. Efficiency, of course, yeah, it have a big relation with the output power actually. So that's if this one have a good performance, means the efficiency of have a good, you know, accuracy as well. And then the phase difference is quite the same, not that big difference. And then the voltage gain also have a big difference. See here, the MFHA can match the the measurement result, especially in the medium to high load conditions. Okay, so this of the waveforms. This waveform we capture in the by using the frequency modulations, and here by the phase shift modulations. And this we try to combine both the phase frequency and the phase shift modulations, because both of them have the advantage. Maybe we can discuss in another sessions for this kind of, you know, control strategy comparisons between FM, PSM, and the combined FM and PSM. So this is the efficiency curve from frequency modulations, phase shift, and the combined FM and PSM. Yeah, so as we can see here, the combined one have a better efficiency, no matter in the 3 cm air gap or the 4 cm air gap. Yeah, because yeah, we do some optimizations to control the phase shift and the frequency at the same time. Yeah. So the conclusion is we do some approach, geometrical approach, to do the to estimate the key parameters of the coil, and then we do the MFHA, modified FHA, to see the operability analysis of the coils. And then we verify by some experiments, burn-in test, 30 minutes burn-in test for the coil, and we compare the FHA and MFHA, and we can see that MFHA have a good accuracy compared to FHA, and also the follow coils, not only have a good performance in the misalignment. Most of the paper will talk about the misalignment, but it also have a promising result for the thermal performance. Yeah, that's all from me. Thank you very much for having me, and thank you very much. Yeah.
Dr. Laska, thank you for your nice presentation. There are some questions related to your presentation. The first question is about the heat problem. Do you think if the coil is too hot, can it be exploded like some situations in iPhone? This is the first question.
Okay. Okay, thank you, Dr. Kim, for all the questions. Of course, it can be burned. Yeah, it can have a sparks, of course. And actually, I burned so many times. Yeah, I burned so many times, maybe more than 100. Yeah, coils burned in. Yeah, so yeah, for the heat problem, it can have a many trouble. Yeah, first have a sparks. Yeah, burning sparks, and then it can broke the enclosure. Yeah, and also harm the AG ferro buds. Yeah, so we need to put the heatsink, aluminum heatsink in the back side of our ferrite. Yeah, so this kind of aluminum materials have two functions. The first is to shield our magnetic field. Yeah, and the second also for for the cooling solutions. Yeah, so before design the coil, we should do the burn-in test to make sure the coil is well performed. Yeah.
There is the second question related to the coil design. How is the coil designed to be the most optimal? I think this question is a little bit broad, but can you tell us about your personal opinion about the optimal design of the WPT coil?
Okay. Of course, the first, we need to know our specs. This is the first things we need to do. We need to know our specs, how big power we want to deliver, and how big size is a load for us to make the coil. Yeah, so that we can do the operability analysis based on the FHA or MFHA to see the performance, like the efficiency. We can check our efficiency is good enough or not. Right, and our power dissipation is big enough or not, like this, and our gain is enough or not. Yeah, because based on the specs, maybe we need to achieve a higher gain. So that means we need to design the sufficient inductance, no matter the self or the mutual. Yeah. So first, we need to understand our specs, and we need to fix some parameters like the size, or like the switching frequency operations, maybe. Yeah, because the higher the switching frequency, of course, your RAC, based on the ferro equations, will be higher. Yeah, so yeah, so maybe after understand the specs, we need to do the operability analysis to see the performance. Yeah, if good, we can try to find the good materials, like we can choose a good ferrite, we can choose a good lead wire, and also it's like a trade-off with the cost, of course. Yeah.
Thank you for your answer. And there are two questions about your experimental setup, I think. The first question is how charging and discharging the battery at the same time affects on the battery. And the second question is that can we power motors directly from the coils without using battery?
Sorry, can you repeat the first questions?
The first question is about is that how charging and discharging the battery at the same time affects on the battery?
Oh. Yeah, of course, it's give a significant impact, but I think the material or the battery engineers will be more suitable to answer this kind of questions than me. Yeah, but
yes.
Yeah, but of course, the battery will have the cycle, right? The cycle time, no matter for charge or dischargings. Yeah, so by doing that in the same times means that we will reduce the cycle charging cycle very fast compared to do that separately. Yeah, so I think it's not a big problem for this kind of AGV applications because mostly they will do charging in the docking stations. That means the robots will not be charged when it discharges. Yeah.
And the second question is that can we power the motors directly from the coil without using battery?
Yeah, I see some research about that. Yeah, because some motors are composed from some, of course, winding, right? Yeah. So some vendor, they make the technology to polarize from the power source to the motor through the wireless. Yeah, but I never do that. I think if the question is possible or not, I will answer it's possible. Yeah, but I never do that. Yeah, and I think you need to consider the cost more for this kind of technology. Yeah, because you need more, ferrite materials to do this. Yeah, and we know the ferrite materials is not that cheap. Yeah.
Okay. Then I have a question related to your presentation. You mentioned that you are researching on different control strategy, and you show us the experimental result in the final slide here.
Yeah.
So could you explain more detail about the other modulation and the experimental result?
Okay. Okay. So these two are the basic control strategy for resonant-based converters. Yeah. The first is frequency modulations, and the second is phase shift. Yeah. So for the frequency modulations, we will change the frequency when the response change, like the load or the V-in or the air gap. Yeah. So when any kind of parameters change, means that the gain change. Yeah. So we need to fix or regulate the gain by changing its switching frequency. Yeah. So yeah, for these frequency modulations, we can fix the duty cycle for each switch for inverter. Yeah. For this S1, S2, S3, and S4 into 0.5 duty cycle. And then we do the frequency control in here. Yeah. So for example, in my design, I need the constant voltage output in a wireless power transfer stage. Yeah. So actually we have 3 stages here. First stage is the pre-regulator, and the second stage is the DC-DC WBT, and the third stage is the post-regulator, the DC-DC pack. Yeah. So in my design, I will keep this WBT DC to DC output into the constant voltage. So that means here I need a phi reference. Yeah, phi reference, and then have a phi feedback here and phi reference. Yeah, to get the error, so we can control. We do the PI control to control this error and do some limiter, of course, yeah, to prevent the over or undershoot. Yeah, and then yeah, we can do the frequency control. Actually, this kind of method is supported by many kind of peripheral. For example, here in the TITSP, they have a EPWM model with this one set of maybe registers to control this whole of this control system. Also like CLA or DP library. Yeah, so in this case, I use the DP library. So the code will be more simple by using this. Yeah. For the phase shift is have the same concept. We also need to regulate the output voltage. Yeah, but instead of doing the frequency modulations, we change the phase shift between to, S1, S3, and S2, S4. Yeah, here we change the S3, S4 phase here and keep the same frequency. Yeah, and the combinations will be like this. Yeah, combinations will be like this. So in this case, we do both together. Yeah. So we do the frequency control, yeah, but we also do the phase shift at the same time. So that means I put another, another loop here to check the PFP. Here is the power feedback. Yeah, I need this to stabilize all of the loop because we have so many loop here. So this the third loop will keep the feedback. The control will be keep more. More slower actually, because if these two loop, I mean the frequency control loop and the phase shift loop run at the same time, sometimes they will, bump each other. Yeah, so we need to organize them by using, the third loop I put here. Okay, but yeah, this combined frequency and phase shift have some problem like this. If the phase shift phase angle is too big, yeah. So you have the switching spike like this. Yeah, this because the main reason of this is when the circuit arrive in this stage, yeah, the power will have a source from the resonance, from the LM, for the magnetizing inductance. Yeah, but the power stored in the magnetizing inductance is over. Yeah, so that's the power is we got the power. After that, we got the power from the COSS, the output capacitance from the MOSFET. So that means that the MOSFET will take care of this stage. Yeah. So the VDS here will be dropped because you discharge more energy from the COSS. Yeah. And in this phenomena, you will get the switching loss. Yeah. So normally you run in the inductive region to get the ZVS for any kind of resonant converter. But if you face this kind of problem, yeah, your ZVS will be nothing. You will get the switching loss from this phenomena. Yeah. So what should we do? Yeah, we should have a balance between the frequency and the phase shift. Yeah. So for the frequency, yeah, you need to have some limit. If you do bigger bandwidth of the frequency control, that means your frequency will be far away from the resonance. Far away from the resonance means your circulating current will be higher. So your conduction loss will be higher too. Yeah. But if you do bigger phase angle in the phase shift modulations, you will get this problem. So you need to have a balance conditions between the frequency control and the phase shift control. Yeah, so this waveform is when you will be happen when you do the the good balance between both strategies. Yeah, so you can see there is no any spike here. Yeah, but also can reduce significant reductions for the circulating current. Yeah. That's why we can cut this curve. Yeah.
Thank you for your answer. Your presentation give us a detailed analysis procedure to estimate the circuit works and your further research. I hope you can get a good experimental result and academic publication. Thank you.
Yeah. Thank you very much.